Hi, my name is Muhammad Rizal Osman. On today's video, I will share with you on modeling of rate-based methane steam reformer in Aspen Plus. As a background, methane steam reformer is a reaction between methane and steam over a nickel-based catalyst supported on alumina to produce hydrogen and carbon monoxide. And since the reaction occurs through absorption on the surface of the catalyst, the rate expression is best represented by the Langmuir-Hinshelwood equation. And if you look at this rate expression, Langmuir rate expression, it combines three terms. First is the kinetic factor. Second, driving force expression. And third, the absorption expression. Based on the theta absorption factors of the reaction components, the overall Langmuir rate expression is shown in equation 1 here. In this equation, there are three terms where K1 is the reaction rate constant that represent the kinetic factor term. This term here is the driving force expression, where K1 is the reaction equilibrium constant. P represent the partial pressure of component I, and the denominator is the absorption expression represented by Dn, where Ki is the absorption equilibrium constant of component I, KCO, KH2, KCH4, and so on. These are the absorption equilibrium constants. The absorption equilibrium constant can be expressed by this equation here, where K equal to exponent A times exponent B over T times T power of C times exponent D times T, where A, where A, B, C, and D are the coefficients. Now, in Aspen Plus, we cannot directly use this expression. It need to be expressed in logarithmic form. Okay, as shown here. This is the logarithmic form of this expression. And if you look at this equation, there are total 4 coefficients, A, B, C, and D. However, only A and B need to be defined, where A is log of pre-exponential constant, whereas B is the activation energy divided by gas constant R with a negative sign here. C and D is normally set to 0. Up to now, I have explained the related equations to model MSR, and now I will describe on the kinetics data. Actually, there are many research done to determine the reaction kinetics using various methods, various catalysts. However, in this video, the kinetics data will be based on our paper Amran et al. And the data is shown in this table. Okay. In this table, it shows the reaction rate constant, equilibrium constant, the pre-exponential constant, and activation energy value along with its respective unit. And this data will be used to model the rate-based MSR reaction in Aspen Plus. However, some conversion is needed as Aspen Plus requires certain form of input. Okay. the reaction rate constant, for example here, need to be in second. So this one is in hour, so need to be converted in second. In addition to that, all you need, particularly the pressure, need to be expressed in SI format. Shown here is the reaction kinetics data after conversion. These two columns here shows the converted value for reaction rate constant and pre-exponential constant, which is now in second and SI unit. Second and SI unit. Okay. Once we get this value, next is to calculate the coefficient A and also B in the absorption equilibrium constant expression, yeah, where A is the log of the pre-exponential factor K, right? This one. And B is the ratio of activation energy over gas constant with negative sign. So once calculated, this data is ready and can be used in Aspen Plus. Next, I will show how to model the reaction using this kinetic data. This is the case example. The flow sheet consists of 3 feed input, a mixer, a heater, and a plug flow reactor. All the feed stream and equipment specification are given in the slide, and we will use that information to simulate the MSR process. First of all, we need to define the component ID. So we have 4 components here, which is methane, and then water, hydrogen, and after that we need to select our thermodynamic model. In this case, we select Peng Robinson and we click next. After that, we go to the simulation section. This is where we will draw the flow sheet. So the flow sheet consists of a mixer, right, M1. So this mixer have 3 input stream. First is CH4, second is steam, and third stream is hydrogen. The input then add to a heater, H1. So we reconnect destination to the heater, and then output from the heater would then fed to a PFR. So this one we select plug flow reactor. We can change the icon to this one. We name it as R1. So we reconnect destination to R1. Then we add the final stream, which is the output stream. So that will be our flow sheet. Yeah. The next thing to do is to define the feed information for methane. The temperature is 25 degrees C, pressure 29.4, mole will be will be your methane. Next is the steam, 25 degrees C, 29.4 bar, 200 will be water. And the last feed stream is the hydrogen. This one is also 25 C, 29 bar, and 4 kilomole. Fraction pure hydrogen. Next, we specify the mixer information. Pressure is 29.4 bar. Valid phases is vapor liquid, right? And then the heater pressure will be temperature is 700 degrees C, and for pressure drop, pressure we put zero means zero pressure drop, and then the valid phases will be vapor liquid. Now next, our reactor type, we put reactor with specified temperature based on the inlet temperature. The configuration will be, this is a single tube with length of 10 meter and diameter of 0.6. And the valid phases will be vapor only, all right? So the reaction, we need to set it up. I will show you after this. Next is the pressure, all right? So we select pressure drop, we specify the pressure drop, which is 0. Okay. And then for catalyst, since we include catalyst inside the reactor, we click catalyst present in the reactor, and we specify the particle density, which is 2355 kilogram per centimeter per cubic meter. Then that voidage will be 0.35, right? Next, we need to set up the reaction. So we go to the reaction tab. Okay, click the folder, reaction folder, to create new reaction ID. Okay, on this tab, we create new, and we enter the ID name, for example, MSR, and select LHHW and the reaction tab. Click OK. After that, we need to specify the stoichiometric reaction stoichiometry. Click new. So we follow the reaction equation here. So we have methane, water, coefficient -1, and the product will be hydrogen and also carbon monoxide. Hydrogen will be 3, and carbon monoxide will be 1, right? So click close. Next, we will need to specify the kinetic information. Yeah? So for this reaction, the kinetic phase will be vapor, and the rate basis will be catalyst base. And you see here the Langmuir kinetic expression. So we need to specify all of these terms: kinetic factor, driving force, and absorption expression. First, we define or specify the kinetic factor here, and we look at the value here, right? Now for reaction rate constant, the converted value will be 3.74 exponent 14. Okay, this value here. And then the activation energy will be 24, sorry, 24,0000 joule per mole. Also we can also use this value, this unit, kilojoule per kilomole. It's the same as the value is the same for unit joule per mole, right? That is for the kinetic factor term. Then we go to the driving force expression. We click driving force. Now we have two terms here. If you look at the expression, right? Rate expression. Okay, two term here. First term and second term. So the basis will be partial pressure. And so we have the term here, CH4B1, H2O B1, hydrogen will be negative 2.5, and CO will be 0. And this value, since there is no coefficient for driving force constant, we set it to 0. Now we add another, we define this second term, right? So this one will have, this is for this part here. Exponent will be 0 for CH4, 0 also for water. But for hydrogen, we have 0.5, and CO will be 1. Yeah? Okay. Now, for the coefficient, this is actually the K1 value. And for this one, we will refer to the value here, the converted value. And for A, since the expression, if you look at it, it is actually 1 over K1. Therefore, in terms of logarithmic value, A will be in negative term, 52.743. Okay, K1, this one, equilibrium constant, right? Sorry, this value here. And also the value of B will be 26,485.446. Okay. So since this is inverse of K1, so we also inverse the negative sign, right? We leave C and D term, coefficient as 0. Right, so this is the driving force expression. So we close it. The last expression will be the absorption, right? So we'll be specify this value based on this equation. All right, right. So the absorption expression is at the bottom here. So the absorption expression exponent is 2, right? Yeah, this two here. And then the concentration exponent is actually this one, KCO KH2. So we have component for CO, hydrogen, and then methane. Lastly will be H2O, right? So actually, what we trying to do is to write this equation, yeah, in the format of Aspen Plus. So this is term number one, this is term number one, term number two, term number three, term number four, term number five. Okay, for term number one, since this is one, so we set uh sorry 0 for all component. Okay, for term number two only exists for CO. We put it as 1 and the rest will be 0. Right. Term number 3 only hydrogen, so that will be 0. Hydrogen, sorry, hydrogen will be 1. This one will be 0. Okay. Term number 4 only methane. Okay, the rest will be 0. Term number 5, so we have 0 for methane, but for hydrogen we have 1. Methane we have sorry, hydrogen we have -1, sorry, because it's in the denominator here. Methane don't have, hydrogen will be sorry, water will be 1. All right, so that is our denominator expression, this term. Okay, so the next one is for us to specify the absorption constant. All right, so absorption constant. Now, next we need to define the absorption constant. So we'll base on this kinetic data, and actually we want to further specify this term, the constant for this absorption constant. Now, we have this is term 1, term 2, term 3, term 4, term 5. So for term 1, the value will be 0 for all since it is 1. And then for the second term, it is only for KCO for carbon monoxide. So we look at the converted value here. So coefficient A is the ln K. So this is the value, -20.931, and coefficient B will be the activation function over this one will be 84971715. Next, the third term, which is hydrogen. So hydrogen, the lone K value will be negative 21.227. This one will be 9971.133. The fourth term will be methane. A will be negative 18.42. This one will be 4604.282. Then term will be water. This one will be 0.58, sorry, 0, 0.558, and this one will be minus 10666.346. All right, so it should be minus here. All right. Okay, then we close it. We have finished define the absorption terms, so we close it. Make sure that there is a right sign here, means that all the input specification is complete. Now we go to the flow sheet. Next we need to select the reaction. Okay, this is one that the reactionary that we have created. We put it to the right hand side, and all the information for this reactor is complete. Yeah? Now actually we are ready to run this process. We go to next, right? All required input is complete, and we are ready to run the simulation. Okay, something missing here. We need to set this to run this one first. Oh, sorry, what happened? Check any problem here. Selected model. Okay. Then so maybe we select. I think this should be okay. Thing component. Oh, okay. So this will be H2O. Right. Redefine there. So careless mistake. Sorry for that. So we go to simulation and we reset again, and then we run it. Right, result available. Then we can go to the input. Oh, sorry, output, and we'll look at the mole flow, and this is the final result. Yep. I think that is all I can share with you. Thank you for joining me, and hope to see you in the next video. Bye bye.